Starting from this week, we will begin to solve new kinds of problems, which ask you to find electric forces or electric fields for charged objects whose size is non-negligible. When we introduced the Coulomb's law for electric force a few days ago, we derived it in a very special case, when all charged objects creating the force are essentially point-like, which means that their sizes are very small compared to the distances between the objects. For example, we took two charges, QA and QB, and we could easily find the force between these two charges using the Coulomb's law shown here. However, imagine we replace charge QA by an electrically charged cloud. What happens in this case? Which formula are you going to use? If you think about it for a moment, you will realize that the Coulomb's law does not work immediately for the cloud. The cloud is not just one point, it is spread over some volume and space. The Coulomb's formula was worked out for 2 point-like charges. It does not apply to such an extended cloud directly. To get around this complication, we will use a very common trick that finds the total force on charge B by integration over all charges in the cloud A. We notice that the Coulomb's law would apply to any portion of the cloud that is small enough to be considered point-like. So we divide the cloud in n small pieces, where n is very large. Any piece has a charge delta Q, and the Coulomb's law applies to the force delta Fi exerted by charge delta Q on B. So we can write down that delta Fi is equal to K times delta Qi times QB divided by the distance between delta Qi and B squared and multiplied by the vector r hat pointing from delta Qi to B. So then we can find the total force on B by summing over all such elementary forces delta Fi. We get a formula on the right hand side which is quite complicated. We cannot solve this formula directly. However, we can take the limit n going to infinity, in which case this formula becomes an integral. So we can find the total force exerted by the cloud A on B as an integral of the forces dF over A. And you can further write it as K times QB outside of the integral multiplied by the integral of r hat from dq to b divided by the distance dq from dq to b squared and integrated over all charges dq. The integral that you saw on the previous page is weird. It is an integral over all elements dq of a function that depends on the distance r from dq to b. We cannot calculate such integrals. Instead, we use another very helpful trick that replaces the integration over dq by integration over the coordinates x, y, and z of this charge dq. Here is where charge densities come up. There can be three kinds of charge densities called linear surface and volume charge densities that are denoted by Greek letters lambda, sigma, and rho. Say, if you take a charged thin rod with a total charge Q and you align it along the x-axis, so then you can define a linear charge density, lambda, which is equal to dq over dx. Then the charge dq at point x is simply equal to lambda at point x times dx. And so the integral over dq becomes simply the integral of lambda x over dx and multiplied by the same function of the distance. Similarly, if a charge distribution is spread on a two-dimensional surface, it is described by a two-dimensional surface charge density sigma that depends on x and y. So the element dq is equal to sigma at x and y at multiplied by dx dy. You get a two-dimensional integration over dx and dy. Finally, when the charge is distributed over a volume V, you introduce a volume charge density, rho, that depends on x, y, and z. The integration over dq becomes the integration over dx, dy, and dz with an additional prefactor of rho. On the previous slides, we talked about finding the total electric force on charge QB placed in point B. Of course, you can easily find the electric field at point B, created by the cloud A. To find the electric field, you simply need to divide the total force on the test charge B by the charge B itself. Since charge B is taken out of the integrals as a common prefactor, you can easily find expressions for the electric fields for a linear surface and volume charge density given by very similar integrals. They don't include QB as an overall prefactor. Let's take a closer look at these integrals. First, let's figure out what an integral of a vector means. On the left-hand side of each equation, you have a vector specified by its three components, Ex, Ey, and Ez. So this means that the right-hand side of this equation also has a vector. If we look inside the integral, we see that the only vector part that can have components is the vector r hat. The remaining numbers are just scalars. So therefore, the x component of the vector E on the left-hand side can be taken by taking the x component of the vector r hat on the right-hand side and multiplying by the all scalar numbers and integrating. Similarly, the y component can be found by integrating the y component of r hat with the other factors. And similarly, for z component, we take the z component of r hat and integrate it over. Before you begin solving the integrals, you should always draw a clear diagram indicating the direction of the total force. You should also try to figure out if any components will vanish after integration. For instance, if the charge distribution is symmetric with respect to the y-axis, the x component of the total force will integrate to 0, because the integral for positive x would cancel the integral from negative x. You don't need to compute integrals for the components that are obviously 0. This can save a great deal of your effort.